Hi there. In this video, we're going to keep going with Chapter 6, and we're going to look at difference in proportions. And don't forget the sections are out of sequence. We're doing both proportion ones together and both mean sections together. So we go 6.1, then 6.3, then 6.2. Make sure you watch the videos in order. All right, let's get started. So this section's a lot like the last one, where we're just establishing some formulas, plugging the numbers in, checking that the samples are large, computing a standard error, and once we've done that, the problems turn into problems from Chapter 5. So for two categorical variables, the parameter of interest is the difference in population proportions, P1 minus P2. The central limit theorem says that sample statistics follow a normal distribution if the sample size is large. Now here we need two samples to both be large, right? Because when you do a difference in proportions, you have a categorical explanatory variable, and that means you have two samples. Or one sample split into two parts, both parts need to be large. So if the sample sizes N1 and N2 are large, then the distribution of difference in sample proportions, p hat 1 minus p hat 2, taken from populations with known proportions p1 and p2, follows the distribution n, p1 minus p2, and se. So this is one number, right? p1 minus p2 is one number. And the standard error, of course, is the variability. So these formulas are very similar to what we saw in the previous section. We're just checking we just have to check them twice, right? Because there's two samples. So we need to check N1 P1 greater than 10, N1 1 minus P1 greater than 10. And same thing, but for the other sample. The standard error looks similar, but it's not the same. Instead of just one of these, we have two of them. And as always, we can use our graphing calculators to build that to look exactly the way we want it to look. If the true values of the population parameters are unknown, then we replace P1 and P2 with P hat 1 and P hat 2 for confidence intervals, or replace both P1 and P2 with the pooled proportion P hat for hypothesis tests. So this is a sort of a theoretical thing, but we've already done randomization distribution, so this will make sense when we explain it. All right, so let's see how to use this formula and this one. Consider random samples of size 58 drawn from population A with proportion 0.71, and random samples of size 72 drawn from population B with proportion 0.61. Find the standard error for the distribution of the sample statistics. So generally speaking, you're not going to have to check if the samples are large, but make sure you could do this if you were asked to do it. So we're just going to focus on the second formula here, the standard error formula. So what you want to do is the same thing we did last time. Build your radical, build one fraction, and then maybe you want to build a second fraction inside there, right? Just to get it to look the way we want it to look, right? So this is what we want it to look like, and that's what I have. So you're going to type in P1. Here we have PA and PB, so we're going to do PA. So it's 0.71 times, oh, that was weird. Hold on. Something strange happened. This app has been acting funny lately. Yeah, I'm just going to go ahead and do them one at a time. So 0.71. Yeah, I don't know why it's doing that. 0.71 times 1 minus 0.71. And that's size 58. And then all you have to do is hit the right arrow. So when you're done typing the 58, it's going to look like this. Just hit the right arrow and then put a plus put another fraction I do not know why this isn't working. There it goes. There it goes. Put another fraction in, and then do the same thing with the second fraction. 0.61 times 1 minus 0.61. And these samples are size 72. So you get this big, gigantic thing, right? And you get 0.083. So one thing I want to point out here, that in the notes, just to keep this thing moving, because our last video was 56 minutes, I don't want to do another 56-minute video, is that really all you have to do is show this step, typing the numbers in, and the answer. You don't have to show these intermediate steps unless you want to. If you're not comfortable typing everything in one shot, I put the intermediate steps in there so you can check your work as you go. It's up to you, though, how you do it. But all you really have to show is this step and the answer. And just round the answer to whatever you're asked around it. Here I did 3 decimal places. So note that we are not dealing with 2 different proportions computed for the same group, such as the difference in proportion of voters who choose candidate A compared to those who choose candidate B, right? We don't have a statistical measurement for that. Remember, we only pick one of the response variable categories as the category of interest, and we call that X, or use it to compute P hat. You don't compare different categories of the same variable to each other. So determine whether the situation involves comparing 2 groups or comparing 2 proportions from the same group. So for part A here, compare the proportion of students who study abroad between those attending public university and those at private universities. So we're comparing the same response variable, category, studying abroad or not, and then we have a categorical explanatory variable here, that's the type of university. So if you have a categorical response and a categorical explanatory variable, that's a difference in proportions. So that would be 2 groups for part A, right? Part B, compare the proportion of voters who vote in favor of a school budget proposal to the proportion who vote against the proposal. Notice we're measuring 2 different categories of the same variable here, right? Measuring who voted in favor and who voted against. Those are different response categories, so we don't compare them. Instead, we would just use a confidence interval or a hypothesis test for a single category. So B is the same group, 2 different response categories. So solution for A is 2 groups. Solution for B is 1 group. Remember, explanatory versus response. If the response variable has 2 different categories, then it's 1 group. If the response variable is 1 category, but there are 2 explanatory categories, that's 2 groups. That's what we call 2 groups, the explanatory variables or the populations, right? All right, let's keep rolling. So let's talk about how to do a confidence interval for a proportion. Notice I'm building all these formulas using that template, sample statistic plus or minus z star times the standard error. And then we just plug in everything we need. The sample statistic is going to be p hat 1 minus p hat 2. Z star, we know how to find that from chapter 5. And the standard error, we just saw how to compute that using this formula here. So to check whether the samples are large, we use p hats for confidence intervals. And what this means is that each sample needs 10 successes and 10 failures. The standard error, we're just replacing P1 and P2 with P hat 1 and P hat 2. And so the confidence interval, P hat 1 minus P hat 2 is our sample statistic, Z star times the standard error, and the standard error is that. Again, don't forget, our margin of error is everything to the right of the plus minus. I didn't have room to put it on this slide, or I would have put it on there. Margin of error, if it's asked for, is everything to the right of the plus minus. That's how it was defined in chapter 3. We haven't changed it a bit. All right, so use the normal distribution to find a 99% confidence interval for P1 minus P2 given the relevant sample results. So P hat 1, N1, P hat 2, and N2 are all given. So give the best point estimate for P1 minus P2. Best point estimate is always the sample statistic. So it's just going to be P1 minus P2. Sorry, P hat 1 minus P hat 2 is 0.17. Find the margin of error. So we want to use the template that we used in the last section, where it was standard error times Z star, right? So the standard error, we're basically going to use that big formula up here at the top for the standard error, right? So just get ready. Got to type a bunch of stuff in. Oop, I messed that up. Here we go. So it's going to be, so we're using the formula on the previous slide, right? Standard error, P hat 1, 1 minus P hat 1 over N1, and then put a plus sign, and then the same thing with the other group. So P hat 1 is 0.78 times 1 minus 0.78. Sample size is 590. Hit the right arrow, hit plus. Put in another fraction. 0.61 times 1 minus 0.61 over 290. So make sure that it looks like what I just typed in. You can hit enter from there. Okay, so you can see our first two, you can barely see 0.17 is still up there. And again, just round this to, I'm keeping 4 decimal places because my final answer is going to be 2 or 3. Keeping a couple extra decimal places is always a good idea. And you can see that I showed some intermediate steps again. You don't have to show the intermediate steps. You just have to show what you typed in. And then the answer. Now that's the standard error. That's not the margin of error, right? To get the margin of error, we need to multiply this by Z star. Z star for a 99% confidence interval is 2.576. And so there's our margin of error. And I rounded it to 3 decimal places. So my confidence interval is just going to be P hat 1 minus P hat 2 plus or minus the margin of error. Those were switched, right? So it's just 0.17, which is my sample statistic, plus or minus the margin of error, which we already computed here. And so you're kind of, again, this is sort of a long method, but it always works. Anything that the homework asks you, you will be somewhere in these calculations. Maybe the homework doesn't ask for a margin of error. It doesn't hurt it. It doesn't hurt anything to compute it. And so the answer is 0.084 to 0.256. So make sure you can get these numbers, pause the video, and check that you can get these results. I'm going to keep moving. 2 proportion hypothesis tests. So here I'm using the template developed in Chapter 5. And we're really just going to do it the same way. Check that the sample is large, if required. Compute the standard error, and then compute the z-score, the standardized test statistic. And when we compare proportions between 2 groups, the null hypothesis is that the proportions are equal. So that means the null parameter is 0, right? So when we subtract, look at it again, look at the formula. This is p hat 1 minus p hat 2, but we're assuming the population proportions are equal. So this is 0, right? The null parameter. And the standard error. So this gives us this. Now, this is just sort of the template formula. You don't have to type in -0 if you don't want to. So the null hypothesis says the population proportions are equal. What would p hat 1 and 2 look like if they came from populations with equal proportions? So let's stop and think about what this is saying. The samples are not going to have the same p hats, because then your sample statistic would be 0, your z-score would be 0, and your all of your p-values would be 0.5. And that doesn't happen too much. So we know that the p-hats are going to be different. What we're asking here is, what would they look like if they came from populations with equal proportions? So that's what you have to think about. In other words, when we're using the formula for the standard error, do we want to use p hat 1 and p hat 2? Or do we want to use a version of p hat 1 and p hat 2 that would be more representative of what they would look like if they came from the same populations? Or if they came from populations with equal proportions. So what we're going to do is we're going to use the concept developed in section 4.2 when we computed randomization distributions for two proportions. The sample data values were pooled and then randomly reassigned to the two groups. And we didn't do one like specifically like this, but that was the concept, right? That anytime you have two groups, you pool, right? You take both sets of data values, you dump them together, and you randomly reassign them. Well, that's basically what we're going to do. So what we're going to do is we're going to pool the data and then reassign it, not randomly, but we're gonna figure out sort of what p hat 1 and p hat 2 put together would look like. And we're going to call that our pooled proportion. So it's like we're going to take the categories and dump them together and not reassign them. We're just going to look at the pooled before it's reassigned. And we called this pooled proportion p hat. And note, this is the same symbol used for a single sample proportion, but it is used when a study has two samples. So this is the only time we reuse notation in two different situations. So if you see this p hat, you have to ask yourself, are there two groups or just one? If there's one group, p hat is just number of successes divided by n. If this is a two-group study like we're looking at here, you have to use a special formula, and the formula is given here. It's called the pooled proportion. Again, we still need to check that the samples are large. I didn't put the formula on here. It just takes up too much space, as you can imagine. If I included every single formula in Chapter 6, there'd be about 70 formulas. So I'm skipping some of them, right? But do notice that we do have this large samples condition. I marked them in green because these use the pooled proportion. So anytime you're doing a hypothesis test with two proportions or a difference of proportions, same thing, you need to compute this pooled proportion first. There's two different formulas for it. They're the same thing. It just depends on what you're given in the problem. If you're given n and p hat, or n1 and p hat 1, n2 p hat 2, use this formula. If you're given the number of successes in each group, just use this formula. Standard error, very similar to what we saw in example 1, we're just using p hat here, not p hat 1 and p hat 2. That's for confidence intervals. For hypothesis tests, anytime you see a p hat, 1 or 2, it's replaced by this p hat. And the standardized test statistic is just this. Again, there's a -0 here, but you don't have to write it. And then we're going to use the alternative hypothesis, the z-value, and the normal CDF calculator function to find the p-value. So this is basically as complicated as it gets. in this course. This is the most formulas we need to use for a single type of problem in the entire class. So I'm only going to do one of these, and then I'm going to show you that shortcut that I showed you at the end of the last video. If you're not interested in the shortcut, skip the end of the video. In 2013, a 16-year-old girl used a science project to investigate whether organic food provided health benefits to fruit flies. She randomly divided the flies into two groups and fed one group conventional food, potatoes, raisins, bananas, or soybeans, and the other group the same type of food but the organic version. She then followed the flies and measured variables like longevity, fertility, stress resistance, and activity. Her results earned her honors in a national science competition and publication in a prestigious journal, and I'm assuming some sort of scholarship, even though I'm not sure. So we want to test PO equals PC versus PO greater than PC, where PO and PC represent the proportion of fruit flies alive at the end of 20 days of those eating organic potatoes and those eating conventional potatoes. And so it turns out that the sample data, 250 of the 500 fruit flies eating organic potatoes are still alive at the end of 20 days, while 130 of the 500 eating conventional potatoes are still alive. Show all remaining details of the test at the 5% level. So what you have to do is really go back, make sure you understand chapter 4 for this. When it says show all remaining details of the test, you're given the null hypothesis and the alternative. So really, we just want to start with the template that we saw in section 6.1 at the end, which is sample statistic, standard error, standardized test statistic, and then p-value and that sort of stuff. All right, so we'll type everything in. The answers are on the next slide, but let's type them in. So first thing up, sample statistic. Well, this is a difference in proportion, so we need p hat 0 minus p hat c. So we're going to have two different, we're going to have something minus something else. Well, 250 out of 500. Oh, jeez. I don't know why it's acting like this. There we go. Minus 130 out of 500. 0.24. So p hat 0 minus p hat c is 0.24. So the difference in proportions, and remember, back in chapter 2, we talked about what constitutes a significant difference in proportions. Well, 0.24 is a pretty big difference, right? And just looking at the numbers, you can see twice as many are still alive, basically. So this is a really big difference. How big? We need to do a hypothesis test to find out. Or a confidence interval would give us the size of the difference, but we're only doing a hypothesis test here. Next up, standard error. So before we do the standard error, let's go back and look at the formula. And I'm not checking that the samples are large. You can see that they're large, right? 250 is bigger than 10. 130 is bigger than 10. Right? These are, so this is fine. You don't have to check this, but you may be asked to check it. I'm just not going over it. There's just no time. So look here, the standard error formula has all these p hats. P hat is this. Well, I don't want to type this in inside this. Let's compute the pooled proportion first. And let's use this formula because we're given x1 and x2. Right? So let's use that formula. Remember, x1 and x2 are the number of successes. In this fruit fly example, the successes are fruit flies who are still alive. So that makes sense. So it's just 250 are still alive in the first group. 130 are still alive in the second group. So what we're doing with the pooled proportion is we're taking both groups of flies, alive ones and dead ones, and dumping them together. So there we're combining the alive ones. In the denominator, we combine the total number of flies. So it's just 500 plus 500. And you can see that it kind of makes sense, right? This is the number of flies alive in group 1, number of flies alive in group 2, total number in group 1, total number in group 2. So we're basically, imagine these flies are like in these containers, and we're just dumping them together. And then, if we had to do randomization distributions, we would randomly reassign alive or dead to the different flies. So it makes sense then that the pooled proportion is 0.38. So if these flies came from the same population, or came from populations with the same proportion of flies alive after 20 days, we would expect it to be around 38% of flies, if they're not messed with, stay alive after 20 days. And so what we're seeing is that, here it's half of the flies are still alive, and here it's 26%. So we can really see how far the samples departed from this p-hat. And this p-hat is what we use in the formula. So we've already computed it. Again, you are allowed to type this in inside each of these, but that just gets horrible looking. Compute this as a separate step and keep like 4 decimals. Now this is 0.3800, right? This is an exact number. But in general, if you get some weird repeating decimal, keep like 4 of the numbers at least. Your lab number 3 uses this technique, and that's what a lot of people miss. In the past, students have missed points on the 3rd lab by not keeping enough digits on the p-hat as an intermediate step. So just keep that in mind. All right, well, let's go ahead and do the standard error. So look here. So it's p-hat times 1 minus p-hat over n1. Well, both of our n's are the same size, and both of our p-hats are going to be the same size. So we're basically going to type the same thing twice. That doesn't always happen. It's a coincidence that it happened here. Right? So 0.38 times 1 minus 0.38 over 500. Right? Because for our fruit flies, n1 is 500. Plus, do it again. And here, n2 is 500. And we're using p-hat in the numerator again, so it's 0.38 times 1 minus 0.38. If you decide that you want to save some work here and there, feel free. I mentioned that in the previous video, that there's a lot of ways to do these problems. When I show you how to do them, I'm doing all the work on every problem. If you decide you want to save a little work here and there, that's fine. You just got to show me what you would type into your calculator. Or just identify the pieces parts. That's fine too. Right? So, you would just have to show what you're typing in. So you get 0.0307. Notice that I'm keeping 4 decimal places for intermediate calculations. That could include the calculation of p-hat itself. Right? Now this is going to be a fraction, but it's just quicker to type in a decimal, especially when you're already typing in big stuff like this. So you may want to round this, and it could be some repeating decimal. So if you get like 0.33333, just keep like 4 decimal places. All right, there's the standard error. Next, we need to use this. So let me go back and show you what I'm using here. I'm just using this standardized test statistic, p-hat 1 minus p-hat 2, divided by the standard error. The standard error is this whole thing, but we've already computed it. If you want to type this whole thing in one step, you're also allowed to do that. I don't recommend it, but you're allowed to do it. So that's what it says here, right? This is the full version of the formula. You don't have to type in a minus 0. We already know p-hat 1 minus p-hat 2 because we already computed it, right? So it's just 0.24 divided by, we already computed this, right? We got 0.0307. I'm keeping extra decimal places for accuracy, right? And you get 7.818. If you round this, watch what happens if I round this to 0.03. So let's say you just rounded 2 decimal places. 0.7818 is not the same as 8, right? Now, your p-value is going to be the same, but your test statistic would be wrong. And this actually happens a lot on the homework. Students will get part of the problem right and other parts of the problem wrong, well, keep extra intermediate digits if you're not sure what you want to do. So there's a right-tailed test because the alternative hypothesis is greater than. It's a one-tailed test. So we just type everything in. And what you get, right, so I'm going to actually show you this one. So it's 7.818. I'm just using a large number here. You can literally type in any big number you want. 0, 1. And look at what it says. It says 2.7089452 e to the e minus 15. Well, you have to write what that is, right? So what that is 2.7 times 10 to the negative 15th, right? That's scientific notation. But most of the time, we round p-values to 3 decimal places. So that's 0. It's not possible for a p-value to actually be 0, right? It can be a really, really small number, but it can't actually be 0. But because we're rounding it, it could be 0 after it's rounded, right? This is a decimal place, 14 zeros, and then a 27, right? And here's the stat key version of it. You can see it's like as far to the right as you can possibly go, and it's 0, right? So this is telling us that it is incredibly unlikely for this to be the result of random chance. You actually have better chances of winning the lottery twice in a row than this being the result of random chance. So that is extremely strong evidence against the null hypothesis, right? And so we would reject the null hypothesis and accept the alternative. And that's what it says here, right? Because the p-value is less than 5%, the results are considered statistically significant. This is extremely strong evidence against the null in favor of the alternative. Now, we are given a story problem for this, so we have to express our answer in context. There was a lot of questions on the second exam about in context. Lots of people missed those. I'm not sure if you don't understand what that means to put something in context. I explained it in the videos. Nobody asked any questions about it, and lots of people missed it. You have to be able to do it. It will be on the third exam. It will be on the final. You must be able to read a statistical study and comprehend what it says in human English. We have sufficient evidence to conclude that a higher proportion of fruit flies that eat organic potatoes will live 20 days compared to flies that eat conventional potatoes. You have to say something like that. So you have to say, statistically significant. You have to say p-value is less than 5% or p-value not less than 5%. You have to express all these, and then if you're given the story going on behind the numbers, like you are here, you have to express your answer in English insofar as that's possible. And last bullet, can we conclude the increased longevity was caused by eating the organic potatoes? So what do you think? Is this causation or just association? I'll let you think about that one. Put your answers in the discussion forum for points. All right, well, that's it for this one. Here's some extra problems for you. If you want to just do it the way I showed you how to do it in the notes, then that's totally fine. You'll be able to do all the homework problems. I'm going to show you how to do the shortcut method for the fruit fly problem. Okay, so stick around if you want to see the shortcut. So let's go back. All right, so how do we do it? Well, as I showed you before, if you stuck around in the last video, on Canvas, in the week 13 material, there are little videos that show you how to do this. I'm just going to show you how to do this problem. If you've been using the shortcut method for section 6.1, it's really, really similar, right? So it's in stat, test. Here we're doing a 2 proportion test, right? So it's under 2 prop z test. We have to type in x1, n1, x2, n2, and then the alternative hypothesis. So it's just it's basically the same stuff you type in a stat key, right? 250, 500, 130, 500. The alternative was a right. Right? Now notice that the p-value is not exactly the same. Right? Oh, it is. It's really, really close. Rounded to 3 decimal places, it's the same. So that's good. It's not exactly the same, and it's because we rounded this. But notice that rounding to 4 here was good enough. Like, this is the same stuff. And you can see that all the numbers we need. There's your pooled p hat, 0.38. So everything we need is given here, right? So there you go. So this was much faster on a problem like this. Computing this pooled p hat, this is definitely a time saver for something like this. For things like confidence intervals, where you have to compute margin of error and everything, it doesn't really save you much time. But for hypothesis testing, definitely quicker. All right, so that's how you do it. Again, there are videos on Canvas that go into more detail. There's those extra practice problems posted on Canvas as well. Katie Dobeck made all that stuff, so all credit to her, of course. And if you have any questions, as always, post on the discussion forum. And that's it for today. And I'll see you next video when we start quantitative response variables, section 6.2. All right, until next video, see you later. And bye-bye.